Welcome everyone to our third episode of Datadog On. This series, we invite engineers from Datadog who are building Datadog on a daily basis to explain some of the nice things that we are building and some of the technologies that we are using. Today's episode is on RocksDB that we will be introducing also during this session. And the idea of these episodes is to be as interactive as possible. So we are going to leave enough room at the very end for questions. So during the session, not at the end, during the session, please use the Q&A button. That you have a button in Zoom with Q&A. Just leave the question there. And at the end, we are going to go through that list and answer all those questions. So feel free to, as you think about a question, add it there, and we will make sure that we address those at the very end. Okay, so probably many of you already know what is Datadog, but just for those who don't know, Datadog is a monitoring and analytics platform that helps companies improve observability of their infrastructure and applications. My name is Ara Pulido. I'm a technical evangelist at Datadog. And there is my Twitter handle and my email. So if you have any questions or feedback about the series or anything, feel free to reach out afterwards. I'm happy to take any other comments, questions that are not specific to today's episode. But today I'm not the important person here. We have James and Kenny today with us. James, can you introduce yourself?
Sure. Hi, I'm James Bibby. I'm the team lead for a team called CoreIndex at Datadog. CoreIndex is responsible for indexing all sorts of primarily string data. We build time series indexes of strings and relationships between them, things like metrics names, host metadata, and especially tags, which is where we chose to implement RocksDB.
Cool. And Kenny, can you introduce yourself, please?
Sure. My name's Kenny House. I'm a team lead on the metrics aggregation team here at Datadog. I primarily focus on our sketch storage systems, including SketchDB, as well as our distribution metrics pipeline as a whole.
Fantastic, thank you. So the first thing I'm going to introduce a little bit is Datadog Scale, because many of the things that we build at Datadog and how we build it are related to the scale we run off. So as a monitoring company, we gather information and we get information from many of our customers' infrastructure and applications. We have more than 10,000 customers, and we gather those data points from millions of hosts. That translates on trillions of data points per day, and obviously that scale introduce a series of problems that we want to share during this series. So RocksDB is used at least 3 services at Datadog, and Kenny and James are experts on 2 of them. So before we continue, I think the first thing that we need to do is to introduce those 2 services so everybody knows what they do and why they're using RocksDB in the first place. So we are going to start with TagDex. James, can you introduce that service and what it does?
Sure. So tags are something we use everywhere at Datadog. We use it to describe and segment data, to categorize data. And TagDex's job is to understand not only all of the tags that exist and index tags as strings, but also understand all of the relationships between tags. So the 3 primary questions that TagDex is designed to answer is give me a list of all tags for a given metric, give me a list of all tags or tag keys for a given host, and give me all metrics for a given tag. And then within there, we have all sorts of support for kind of Boolean logic. So give me a tag that's been seen for a given metric along with these other 4 tags. And we have kind of full text searching and filtering built into all of those questions as well. If you think about what we see as input most of the time is like a single Datadog data point. So some common things that we're interested in that data point, there's a time that it arrived, there's some kind of a value for it, and then there's a whole host of tags. And there could be, just some simple tags like this, or there could literally be, hundreds of tags attributed to one of these data points. And so when we see one of these, and we see a lot of them, as I hinted at the beginning, we want to take all those tags, split them apart, and start to create an index that we can search later. And so the way we have that implemented is with two different RocksDB databases that are correlated. So we have TagDB, which is on the surface really just a big string interning list. So when we see a new tag, we give it an ID, and we create an entry. And we also have a reverse index as well. And we build some n-gram indexes and things on there to help with searching. But the primary role of TagDB is to be able to translate an integer to an actual string, and a string back to an integer again. And then that feeds into TagSetDB, which is where we store those relationships. So for a given tag, let's say tag ID 1, which is the host tag at the top there, and a given metric, what are all the different tag IDs that we've ever seen that with within a certain time frame? And so we use roaring bitmaps for that. I'll talk a little bit about why after, but we use a roaring bitmap to store in the value side of our key value store all of the different tags that single tag has been seen with. And the reason that we use roaring bitmaps on the right-hand side is to be able to enable all that kind of Boolean query logic that I was talking about. So we can go to the next slide. There's a bit of a diagram of how we use that. So if we get a query that says, I want to see for this metric, for this time frame, I want to know which tags were seen with envprod and host web server and app-g unicorn. And so we go and get the roaring bitmaps for each of those, and we can do simple Boolean logic and just ask roaring to, let's say, do an and across those three bitmaps. That returns us the tag IDs that have been seen with all three of those tags in that time frame, and we get this result of Team Web Backend, Role API Server, and Platform Python. We can do other things with ORs and also nots. There's a whole bunch of Boolean logic that kind of comes with using roaring bitmaps. So that's what you see on the right-hand side. So that's in a nutshell what TagDex does. And we use RocksDB as the storage engine for all of our KV stores in there.
Cool. What about SketchDB? Because SketchDB is a key part of our distribution metrics, isn't it?
Sure. So distribution metrics are a component of Datadog that can answer some slightly different questions than you may have seen before with your traditional monitoring environments. So SketchDB is one of several services that powers our distribution metrics pipeline. So in particular, distribution metrics let us answer questions like, what was the P99 latency across all of my serverless functions over the past day? This is something we see a lot of customers using more and more as they're interested in using percentile-based metrics in order to get a better gauge of what the actual end user experience is like with their applications. So in talking about SketchDB, we should first talk about what a sketch is, because that may be a term you haven't run into before. So sketches is a general term for both a data structure and an algorithm. Sketches represent a stream of data, so sketches are used to more concisely encode information about many, many data points. So there's lots of different types of sketches, but in particular for SketchDB, we're interested in quantile sketches. So this is a sketch that can represent with some amount of accuracy that we know, perhaps the P50, P99, P999 of a data set. So the specific sketch type that we're using with SketchDB is the distributed distribution sketch, or DD sketch for short. If you'd like a really deep dive on DD sketch, there was a great article about this on the morning paper that dives into the algorithm I'd encourage you to read. The important points for SketchDB in particular is that DD Sketch is fully mergeable. So this means that we might be receiving sketches from many hosts, many serverless functions or containers. All of those can be merged together to give us a complete picture. We also have relative error guarantees from those sketches. So looking at a bird's eye view of how the sketches arrive to SketchDB, you might have many hosts running in your infrastructure. Those are, say, receiving requests that are instrumented with distribution metrics. The Datadog agent will then package up all those data points into a sketch along with some tags. It's going to send those to Datadog's backend, which eventually may get to SketchDB. So for SketchDB, the kinds of data points we're concerned with are slightly different than with TagDex. So we similarly have a timestamp. But instead of a single value with SketchDB, we're looking at a more complex data structure with multiple values for the sketch. So at least the min, max, sum, count, and a bucketed histogram that helps us describe the quantiles. And then additionally, there's a series identifier that corresponds to those tags that James was just talking about. So in terms of the types of queries that SketchDB is responding to, typically, a query will come in for a particular metric, a time range that the query is interested in fetching data for, the series it wants to know about, as well as the quantile. So what SketchDB is responsible for doing is taking all of those many sketches that correspond to this query, merging them all together, and then returning back a response that includes just the relevant timestamps and values. So for some perspective on this, a single query can often cover many hundreds of thousands, if not many millions of sketches, depending on the time range queried. So some considerations when we were building SketchDB. If we can go to the, so SketchDB, it's a time series database. So this has a couple of implications for us. SketchDB was going to mostly be writing data. It needed to be optimized for writes of recent data in particular. And then additionally, with it being time series, most data is never read. And the data that is read tends to be recent. A second consideration was that SketchDB was going to have a variable data size. So some type of data store that used, say, a fixed schema size that couldn't accommodate these varied data sizes was not going to be a good fit for SketchDB. And then lastly, from a read perspective, SketchDB needed something that could execute really fast range queries. So in general, SketchDB was going to be fielding queries that would cover a range of data that needed to be looked up and read. And so all of those factors combined led us to looking at RocksDB for SketchDB as well.
Cool. Now that we have the introduction, and I think Kenny did something. You were talking all the time about building SketchDB. So brings us to introduce RocksDB. And one of the things that I was surprised to learn about, and I think this was James' definition of RocksDB, is that it's not a database, it's actually a toolkit to build a database. What does it mean, James?
Sure. So when you download RocksDB, it's not like downloading a traditional database that comes with, you know, some kind of a query language and some kind of a schema definition language and you know, some operations and maintenance tasks and dashboards. RocksDB is really it's a library, it's an engine that you can use to build your own database. So you can write arrays of bytes into a key and arrays of bytes into a value. And that's at the top level, you know, what your database entails. There's all sorts of amazing tooling underneath for managing how you search and index those values. But there's no query language, there's no, you know, index capabilities. If you want an index, you kind of have to build one. Like, for example, we wanted to implement full text search on tags, and we just went ahead and implemented our own n-gram index on top of, you know, and using RocksDB.
Cool, interesting indeed. So it's RocksDB is open source. It was originally and it's maintained by Facebook, and it's based on LSM Tree algorithm. What's that, Kenny?
Sure. So James was mentioning with RocksDB being a toolkit to build your own database, one thing you need to stay aware of if you're using it is the implementation details under the hood, because the better you understand those, the easier it's going to be to work with. So in particular, a few things about RocksDB is that it uses this LSM Tree Architecture. So writes in RocksDB don't go straight to disk. They're going to an in-memory mem table. So writes can be really fast because they only go to this in-memory structure and then a write-ahead log that's optimized for writing quickly. So periodically, data is persisted to disk from this in-memory data structure by a background process that RocksDB manages in the normal case. And this process is known as flushing. So as long as RocksDB is able to keep up with flushing data to disk, you're going to be able to continue writing to that in-memory structure. So the data is stored on disk in immutable table files. So as your data grows and grows, as more data is written, RocksDB has a background process called compaction that's going to merge together many of those on-disk table files, combine them, and then write them to what's referred to as the next layer in the LSM tree. So LSM stands for log structured merge. So that's what we see here in the diagram, where data is written to this in-memory log-like format, and then the data is periodically merged together and combined into these larger and larger levels. So an important takeaway from this too is the different levels of the LSM tree can be something you have to be conscious about. An individual query might need to go between lots and lots of files on disk in order to actually find the data it's looking for.
Cool. So a little bit of history, because I know SketchDB was almost built directly on RocksDB, but TagDex had to go through a migration. James, can you talk a little bit about LevelDB, how we were using it, and why we moved?
Sure. So LevelDB is also an embedded persistent key value store. It was written by Google, I believe originally for the Android operating system. And it was based on an LSM tree as well, and some of those original LSM papers. And TagDex originally was written on top of LevelDB. At some point in time, Google or Facebook actually forked LevelDB to create RocksDB, and it was really focused on high write throughput, large data sets. An understanding that it would be backed by really fast SSD devices, and it had some other features like merges, which was especially important to us. And so we went through a migration. It was probably one of my first big projects here at Datadog. I worked on migrating from LevelDB over to RocksDB to take advantage of some of those benefits, because it really was designed for our type of use case. One of the primary kind of bottlenecks in our LevelDB database was because we're using those roaring bitmaps as keys. Every time we see some new tags, we need to go and read the existing roaring bitmaps that exist for that metric and tag combination, add our new values if there are new values, and then write that back. So every time we had to write, we had to do a read, deserialize a roaring bitmap from bytes, or in the new values, and then serialize it to bytes again and write it back to LevelDB. So it was a real bottleneck for our write speed, and so we wanted to move to something that RocksDB offers called a merge operator. And so with the merge operator in RocksDB, you get the ability to really just pile up a bunch of merge operations. So as we're getting new values in, we just ask RocksDB to merge these when it needs them. And there's kind of two times when that might happen. Once is when a compaction cycle happens. It might take up to 100,000 of those pending merge operations, so a whole bunch of roaring bitmaps that are waiting to be merged. it will ask you to merge them and then write the final operation or the final value once into the database or onto that disk-backed persistent storage. The other time that it might do this merge operation is if a query comes in and actually needs to access one of those keys. Rocks will understand that there are pending merges for that key, execute those merges, and give you a final value back out. So what it resulted in for us was the ability to write a lot faster. Because our application really is write throughput focused, the number of writes that we get of points in a day compared to the number of queries that we actually service is orders of magnitude different. And so this is an example from one of our services that moved from LevelDB to RocksDB. You can see the number of kilobytes actually being written to disk decreased significantly when the merge operator was implemented. So it allowed us to process a lot more data with a lot less hardware, a lot less machines, much faster and more efficiently.
Nice. Always good to see those graphs improving suddenly. But it's not only merge. I think it's not, obviously that was a little bit the driver of moving to RocksDB, but there are other nice features like the Prefix Iterator, where if you have a key with a certain pattern in RocksDB, basically it's optimized to move around those keys, those prefixes of keys. And I think that feature is both used by SketchDB and TagDex. James, can you talk us about how you use it on TagDex?
Sure. So this was like an unforeseen benefit of moving to RocksDB. We had always wanted to be able to answer the question in TagDex. Given a certain tag, what are all the metrics that submitted that tag? And it's a question we got from customers really often, and there wasn't really an easy way to answer that question. We would have to navigate the entire database because of the way our keys were structured and because we didn't have things like prefix seeks and prefix iterators. So our original TagDex key was the concatenation of a customer ID, a metric ID, and a tag ID. So there's 8 bytes, and 4 bytes. And so if we wanted to, for a particular tag, find out which metrics had submitted that tag, you can see that those two pieces of the key are disjoint. And so what we did is we actually changed our key structure. And when you're building your own KV store, you can do these kinds of optimizations. We reversed the metric and the tag position. So we had customer ID, tag ID, and then metric at the end. And when you mix that with the prefix iterator, so you set up a prefix extractor in your database that whenever you write a key, it knows how to pull those, in this case, first 16 bytes or first 12 bytes out and create a Bloom filter for that so that it understands how to find those quickly. And underneath, everything is stored in an ordered fashion, so it's very quick to navigate keys that are in order. So we could now just say, okay, give me a prefix iterator. I want this prefix, which is the tag ID we're interested in and the customer that we're interested in. And then all we have to do is iterate over that prefix. We don't even need to read the values. We just read the last 8 bytes, which is the metric ID. And that gives us a list of all the metrics that ever submitted that tag. So we went from something that might have been 20 or 30 seconds to answer to milliseconds to answer. Thanks to the prefix iterator, and got to answer a question that a lot of customers have been asking us to answer in an easy way.
Nice. How about same feature for SketchDB?
Yeah, so for SketchDB, almost all of the queries by the nature of the query are going to be range or iteration queries. So for SketchDB, it was important for us to be able to quickly jump to the start of the data that the query needed to fetch. And then also, as I mentioned earlier in that LSM tree, we needed something that was going to be efficient for RocksDB to be able to quickly check a bunch of other files on disk and see if there was relevant data. So with SketchDB, we have this prefix with the time window, the customer and metric, and then we're able to iterate through all of the data. In addition to prefix iteration, RocksDB also uses prefixes in the way it builds Bloom filters, which helps it when it needs to navigate through those different layers of the LSM tree and check for data. I do want to talk about too, we had a bit of a key migration change with SketchDB as well. With SketchDB, we initially didn't have this time window prefix on our keys. And we were a little hesitant at first to add another component to the keys because this was going to add potentially more data to every key, every value that we're storing in the database. RocksDB, though, very intelligently delta encodes all of the keys. So if you have a common prefix across most of your data, it's going to be stored very efficiently because RocksDB isn't storing that entire key most of the time. So what this time window allowed us to do as well was to align our write patterns better to what RocksDB was doing under the hood. Let's see, if we jump to the next slide, we can kind of see. So most data for SketchDB is going to be written to the most recent time periods. So these time windows allow us to make sure that most data is being written to a time window with the same key prefix. That means that in the background, RocksDB is able to work on all of this other data with different key prefixes and background tasks like compaction and flushing are going to be much more efficient because we're not actively writing to that same time window. So we saw pretty big gains in terms of the compaction timing and CPU use for compaction just because of changing our key format. And I think that was an important lesson for us working with RocksDB is the more you think about these background process, the more you think about what RocksDB is doing under the hood, the more efficient or faster you're going to be able to make your data store.
Nice. The other nice change from the migrating from LevelDB to RocksDB in the case of TagDex has been the ability to do faster backups through checkpoints.
Yeah. So when we were originally running on LevelDB and the version we were on, at least, there wasn't a great way to take a consistent snapshot for backup purposes of a LevelDB database. And so what we would have to do is open up, take a snapshot iterator, which is a guaranteed point in time iterator for the database, and across two data stores, because we really needed TagDB and TagSetDB to be backed up in a consistent manner. So we would take a snapshot iterator from each of those, and then actually physically write all of the data points into another file. And when you're getting into, each server might have multiple gigs of data, tens of gigs of data, it was really slow. Sometimes backing up an entire snapshotting an entire database could take 20, 30 minutes. RocksDB has a really smart way of doing this because all of the files on disk in an LSM kind of backed database are immutable. You can actually just take a hard link of the files and then we could copy that out to cloud storage. So we went from snapshots taking up to like 30, 40 minutes to under a minute, and like 99% of that time is uploading it to cloud storage. The actual checkpoint is milliseconds on the file system because they're just intelligently taking a hard link and giving you a guaranteed access to that file.
Cool. So one thing that I wanted to make sure that we cover on this session is using RocksDB in let's say a Go shop like we are, because RocksDB is written in C++ and as we said, is maintained by Facebook, but they only maintain an official wrapper for Java. And Datadog, most of our backend is written in Go. So how you can combine those two worlds together?
Sure. So there's an excellent library, open source library, which provides bindings between Go and the C interface for RocksDB. So RocksDB is written in C++, but they provide a C interface, and via CGO you can call those you can call that C library. We found Go RocksDB, and we're able to use that as an amazing library to interact with RocksDB without having to write our own. So it's a great open source project. We try and contribute upstream to that as well. So we added the partial merge multi operator, so we're trying to contribute back up to that. But we make heavy use of that library. But that said, there are definitely challenges to using CGO for something that is so important and such a central part of our application. CGO is not free. So although it's an excellent way to be able to access like native C and C++ libraries, from your Go code, there's a lot of thought that needs to go into it. Quite often, the default way of moving information across that CGO boundary is mem copies. If you use kind of just out of the box toolings, you're going to be copying a lot of memory. And when you're talking about a high write throughput data store, copying that much memory around is pretty costly. So you need to really write some unsafe code to be able to pass pointers to memory between the two. And the other real challenge that we've had is that once you kind of cross the CGO boundary, you lose a lot of the amazing tooling and profiling options that Go comes with, and is probably part of the reason that it's used so prolifically at Datadog. Things like inspecting memory and taking profiles, it all kind of stops at that CGO boundary, and it's very difficult to get underneath there and see what's going on with RocksDB's memory usage. So you've got to look at other tools like Jane Malik and some other kind of C visualization tools to try and get access to what's going on underneath, or as we frequently do, kind of eliminate everything else first, and then dig into the more expensive job of profiling that C++ code.
Also, another challenge is that I think we've talked a lot about the difficulties of building this SketchDB and TagDex, because RocksDB is a toolkit and you have to build all those things on top.
Sure, yeah. I think tagging onto the discussion of Go and C++ interaction as well, RocksDB has a lot of places to plug in. So the merge operator that James was talking about earlier is a great example. You provide a function to be executed when a merge happens. That gets compiled into your service, and then that's executed right alongside other RocksDB code by RocksDB. Writing this kind of code from Go presents additional challenges. The same code written, say, just in C++ or the same algorithm might end up being efficient, but once you're crossing back and forth between the CGO boundary, you might have to rethink the way either you structure your queries, how you batch things. All of these factors start to come into play. So building new query types is going to require a lot of careful work. You're going to need to tune it and benchmark it. And so that's something I think all of our teams using RocksDB have had to build our own tools to make sure the types of queries we're executing are being performed efficiently. And so this is a real contrast to, say, a SQL database where you might have a planner that you can see, oh, it's going to use this index in this way and execute it efficiently. You have to be thinking about those things yourself. Similarly, indexes are something that RocksDB isn't going to provide for you beyond just making sure you can seek to the key you need quickly enough. So as you're layering more complex queries, as you're trying to make those efficient, you end up needing to build indexes on top of your data. And so this is something that factors into your write throughput because you're writing more data. It's also more occasions you have to think about, how am I structuring my keys for this index? How am I caching the data for the index versus the main data set? All of these are things that RocksDB gives you lots and lots of options for, but it's definitely an additional challenge when you're working with it.
I think it's also one of the most enjoyable parts of working on RocksDB, though, is that you know, in a typical database, you know, an out-of-the-box relational database, you might just, you know, set up a bunch of indexes and not really think about what's going on underneath. You're not going to think about how you structure a key when you're writing it to an array of bytes underneath. And on Rocks, it kind of forces you to think about all those things and actually understand a lot more about how a database works and the different trade-offs and choices that you make. It's definitely led to me reading a lot more kind of open source database code, just to understand how other people make these decisions.
Cool, nice. Which brings us to the last thing that I wanted to cover, which is cross-team collaboration, because you two are from different teams working on different services. And for example, at Datadog, we were not using RocksDB at the beginning of 2019. And by the end of the year, at least 3 services from 3 different teams were using it. How we move from 0 to 3 services using the same technology, it was a coincidence, or it was like collaboration between the different teams? How did that happen?
I think that there was a lot of chat on Slack about RocksDB from a few different teams. We use Slack a lot for technical discussions and sharing tools and sharing performance wins and learnings. There were some papers that had gone around, and there were some discussions happening. And it seemed like a really, really good fit for us, primarily because of the merge operator. So we'd kind of started that migration, and there was another team with very similar challenges to us, and we formed a RocksDB channel on Slack, and now it's quite active. It's where we discuss kind of pros and cons, findings, performance, wins and challenges. So there's been a lot of communication about it, as well as a number of brown bag talks and demos on it. So for us and one of the other teams that implemented, it was a bit of it's just a bit of timing. We both had the same challenges. We were both on Level DB, and we collaborated over Slack to come to the right solution. I'm not sure how it went for you.
Yeah, so for SketchDB, it was a little bit different because we were building SketchDB from the ground up. So we didn't have a prior code base to be working with. One of the things we factored in was we saw a lot of other teams that were getting more interested in RocksDB. It seemed well suited to these different problems that other teams were tackling that had some similar constraints, but were either slightly different types of data. And then I think a lot of the collaboration on Slack was definitely useful as well, because we might have a slightly different problem, but someone else would have seen, oh, RocksDB has either this option or this API that might allow you to use that for the service you're working on. So particularly for something like RocksDB, where there's just so many options, so many different features and design considerations when you're using it, having a broader group of people looking at the RocksDB code base, experimenting with it in their own services has definitely helped out tremendously.
Cool. Are you doing any regular meetings or anything to discuss this topic? So it's more like ad hoc once you have an issue or you want to share something?
I think like an interesting thing about Datadog is we're quite a distributed group of folks. I mean, we have engineers around the world. And so a lot of things happen asynchronously, but they're quite engaging conversations that happen asynchronously. We definitely get together for things like brown bags and talks and demos and show other engineers at the company what we're working on. But we don't have like a once a week kind of hour-long meeting about RocksDB or anything like that.
This is what we had for today. We still have a lot of time for questions, so please use the Q&A window to ask many questions. We have a careers page, datadog.hq.com/careers. So if you think these problems are interesting and you want to join us, please go there and see if there are any roles you might be interested in. So I'm going to stop sharing my screen now. I'm going to go through some of the questions that we have. The first question would be related to the Go relationship. So working with Go, would you choose Go again, or do you think something else is better for using RocksDB?
That's a. Do you want to field that one first? That's a difficult one.
Sure. So at Datadog, we already had a great culture of tooling and understanding around Go. And so I know for SketchDB, it was a natural choice to implement it in Go at first because we were able to better understand how we were going to use RocksDB. And that let us develop very quickly using Go. So you know, I think in terms of being able to get a service up and running, understand how it works, Go with RocksDB worked out really well for us. You know, there's definitely challenges with it. And, you know, it's certainly a conversation we have in our RocksDB channel and among teams as to whether we would, if we were writing a brand new service, would we use it in Go? If we were rewriting something, would we use Go? You know, again, the trade-offs are hard, and we've been able to write services that are performant and meet our needs with Go and RocksDB for sure.
Yeah, I think that the one thing I would really want to take a close look at when starting, if we're starting a greenfield project, is where is the boundary? So what is the boundary going to be between our Go code and our RocksDB code? And if there was logic where a lot of memory was going to be moved back and forth, I might push a little bit more of that into C++. So we're looking at things like implementing our merge operators in C++ rather than Go because they're called so frequently. So I think it's not that I wouldn't choose Go, it's that I would spend a little more time, and we're spending it now, to see if we can move that boundary a little bit and really optimize how many times we're crossing that threshold.
Makes sense. Another question is, how do you choose what service to move to RocksDB? Is it particularly useful for one more than another?
I think for us, we had extremely high write throughput needs. We have far fewer queries, but they need to be extremely low latency queries. And we wanted the write throughput guarantees, and also to be able to have that fine control over the indexes that we're writing, the way that we write keys, how we store things underneath. I think in order to meet our performance targets, we really had to be able to control at a very fine level what the data store was doing, how it was accessing data, and how it was writing data. So for us, it was about meeting performance needs and also really fine-grained control so that we could implement the queries exactly how we wanted them.
Yeah, I think to add on to that, it's definitely considerations around the request response. What's the data types you're working with particularly? If you have a service that needs some type of data store where the schema is going to potentially change frequently, RocksDB might not be the best choice because that's something you're going to have to manage at your own application level. So that can be a consideration, and certainly the sort of balance of write throughput and read throughput. And I know for many of our teams, we're working with time series data or some variation of that. And so that's definitely been a factor, and RocksDB has worked well for that.
Good. Another question that we have, which is very interesting. You discussed backup times, but what about restore time?
Oh, so for us in TagDex, we take we're a time series database, so we have a new window, let's say every hour or some time period where a set of data becomes static. we're never going to go back in time and need to enter data into that time window. And so when a time window completes, we move just that time window to its own location in cloud storage. The restore is literally just copying those files back into a folder and opening RocksDB again. So there's no, we make sure that we do things like compact and make sure that there's nothing left in the write-ahead log. For that window, it's complete, and then we move the entire thing to cloud storage. Opening it is literally like a 1 second. Once you download it, it's 1 second to reopen one of those windows. So there's not really a long restore time.
Okay. What about reliability? How's been performing RocksDB? Did you have any important outages, or has been working fine so far?
So for us, it's definitely been a performance improvement over LevelDB. Like, I mean, you saw for one of the other services, like an order of magnitude almost decrease in writes per second that needed to happen. It's not something that goes down because RocksDB has a problem. If we have any kind of an outage, it's usually something that we've done. So we've had really, really good experiences with the reliability of the core of RocksDB itself and the way that we use it. I know there's other people out there that have other stories, but our use case has been really solid. RocksDB has never been the problem.
Yeah, RocksDB. I know with SketchDB, we've had times we've tried either different write patterns or key formats, and sometimes can find writes stalling is the term RocksDB uses, and that's almost always been a change where we weren't working well with what RocksDB was trying to do for us. So RocksDB does expose a lot of statistics about what's going on under the hood, and so that's been something really advantageous because it's pretty easy for us to deploy some new code, take a look and see immediately is our compaction flush throughput the same as it was before? Are we seeing more hits on the Bloom filters? Are we seeing less write stalls or no write stalls? All of that is exposed from RocksDB. And so instrumentation definitely becomes very important to making sure, not necessarily that something doesn't fail, but you're not seeing a performance regression or something like that.
And then, of course, we take that data and feed it into Datadog, and so we get it on our dashboards and monitors and alerts. So you can get all of that data out of RocksDB, and then you can send that data to something like Datadog and be able to visualize in real time what's going on in your database.
Which brings us to the next question that we just got, was about monitoring RocksDB inside a service like Datadog. So is there anything specific that we've built inside Datadog for this, or something else?
I don't think, not specifically. There's not like a RocksDB integration, but I think that's because it's not really a kind of commercial database that would warrant an integration. There are a number of metrics available to you inside RocksDB, and you can output those pretty easily to your agent. Although it's maybe not a bad thought. I don't know if you guys have anything like that, Kenny.
Yeah, so RocksDB does expose a set of statistics that it's a sort of unusual format that it's output in, but you're able to get all of the metrics that RocksDB would expose either in log lines or something like that. So all of those metrics I was just talking about, we periodically grab that statistic string, break it apart, and then send it as gauges to the Datadog agent. And so it's really quick to explore all of those that are available because they're all in sort of a common format from RocksDB. But that's been our primary means, and we trying to think. I don't think we've implemented anything custom beyond that. I know you can hook into more of the RocksDB events and lifecycle, but we haven't done anything like that yet.
I think part of that is probably because of that boundary as well. Not everything in the C++ library is exposed in the C API, which means it's not all available to Go, and so sometimes you have to work around that life cycle of C++ to C to Go RocksDB to your library.
Sounds good. I don't think we have any more questions unless you want to have some final thoughts.
Sure. I think that if you're really considering, implementing your own KV store or building your own database on top of this, I would go and spend a lot of time taking a look at first the actual RocksDB code. You don't have to read the entire code base, but understanding the great docs that they have on their wiki page on GitHub, and understanding what the code is doing in some different places will help you build a better data store on top of RocksDB. It's not kind of a blank library that you want to just call the public API of. I think you want to spend time understanding all of the configuration options and actually read some of the underlying C++ code. Really think about that boundary. If you're going to write in something like Go, where there is that boundary, then you've got to think about that. But it really is it's been an excellent library for us. It's been an excellent way of building a database that can stand up to the performance requirements that Datadog has. Fantastic.
Thanks a lot, Kenny and James, for coming here and sharing your expertise in RocksDB. It's been super helpful also for me to learn a lot of how these systems work. So thanks again, and we will have a next episode on Datadog on next month.
So
thanks everyone.
Thank you. Bye.